Hello, I'm Gopal Peddinti from VTT Finland, and I'm presenting the poster titled Timegated Raman Spectroscopy and Machine Learning for the Detection of Common Contaminants in Algal Cultivations. I'd like to start by thanking my co-authors, Jari Haavisto, Anu Tamminen, Mervi Toivari, and Dorothy Barth for their excellent collaboration. The objective of our project, which is called ROBA, which was funded by Business Finland. ROBA stands for Robust Algae Systems, is to develop online measurement technologies and machine learning based data analysis methods to facilitate real-time monitoring of algal cultures. And the specific focus of this study is the use of these methodologies for the early detection of biological contamination in the bioprocesses. In this study, bioreactor cultures of the green algal species Chlorella vulgaris are grown with or without contaminants. Each contaminated culture in the study included one of the 7 species listed on this slide. We have collected training and test data to build proof of concept machine learning models. The training dataset included 14 pure algae cultures and 14 contaminated cultures, having one of the 7 contaminated species alongside Chlorella vulgaris. The age of all the cultures in the training dataset was the same. The test dataset included 10 pure cultures and 8 contaminated cultures, wherein the contaminant species were either Tetradesmus obliquus or the cyanobacterium species mentioned in the previous slide. The age of the cultures in the test dataset varied from 1 to 12 days. The value of Raman spectroscopy in monitoring the bioprocesses is being increasingly recognized. In this study, we use time-gated Raman spectroscopy technology developed by our partner, Timegate. For the machine learning, the spectral data were used directly without transformation or with one of the 3 transformations mentioned here. And these 3 transformations include the normalization of the spectral data with respect to the intensity of the water peak normalization followed by calculation of first derivative, or water peak normalization followed by logarithmic transformation. The untransformed data and the data transformed with the first derivative are shown as line plots on this slide on the left and right hand sides respectively. The water peak region is highlighted with a blue rectangle on both the plots as well. A standard chemometric model called partial least squares discriminant analysis, commonly referred to as PLSDA, was applied for binary classification of the cultures into pure versus contaminated algae cultures. The figure on the left-hand side shows that the data transformed using the first derivative performed best in classification as per the area under the rock curve, called AUC, obtained during PLSDA training. The PLSDA scores plot shown on the right-hand side shows the pure cultures as blue circles and contaminated cultures as orange triangles, and shows a clear separation of classes. To get a more quantitative as well as unbiased estimate of the prediction performance of the model, we used a repeated k-fold cross-validation and obtained an average AUC of 0.78, indicating a good predictive performance of the PLSDA model. Finally, the performance of the model was also evaluated by independent test dataset, which was unseen during the model training. The figure on the left-hand side shows the rock curve on the test dataset showing a high AUC of 0.9 with the 95% confidence interval of the AUC indicated here. On the right hand side, the prediction accuracy is shown as a confusion matrix, showing that most of the test samples are correctly classified. Here, along the rows, we have the original labels, and along the columns, we have the predicted labels. Given that the current results are encouraging, we are collecting more data to be able to apply more advanced machine learning models. With this, I would like to conclude the presentation by thanking our funder, Business Finland, and our collaborators. And I thank you for your attention.